Okay, in this video, we're going to talk about velocity versus time graphs and acceleration versus time graphs. And we're also going to talk about how we go from, let's say, a position versus time graph. How can we construct a velocity versus time graph? How can we look at a velocity time graph and maybe figure out how far an object has traveled? Or we can also look at a velocity versus time graph and determine what an object's acceleration is. Things like that. So really just trying to interpret graphs and be able to construct one graph from another. So these are our standards. You can read through those for yourself. So the goals here, we want to use data or information about an object's motion to construct velocity and acceleration versus time graphs. We want to construct motion graphs given other motion graphs, and we want to determine unknown quantities using slope, intercepts, asymptotes, and area. So here we have three different graphs. We have a position graph, a velocity graph, and an acceleration graph. And what our goal is really is, given any one of these three graphs, you should be able to determine what the other two would look like. So I already have them here for you, but there's a process for determining values from a particular graph. So if you're given position graph, there is a way to figure out what the velocity graph should look like, or what the velocity might be at some given point in time. And also, if you're given velocity, there's a way to go backwards and figure out what position might be at some given time. Okay, if you're given velocity versus time graph and you want to figure out what acceleration might be, there's a way to do that. If you're given acceleration and you want to go back to velocity, there's a way to do that. And the process for doing that for either position velocity or velocity acceleration graphs is the same. So we're mainly going to deal with position and velocity because I think those are conceptually easier quantities to think about. But the process is going to be the same if you're trying to figure out acceleration. Okay, so for a velocity versus time graph and acceleration versus time graph, you graph them on the vertical axis, those quantities, velocity or acceleration. Time is still on the horizontal axis. Remember, AP wants to see you label your axis with units and appropriate increments. I'm not putting any increments on these graphs because we just want a qualitative understanding of what's going on here. So let's look at an example. We've seen this before. How do we get velocity from position from this motion dot diagram? Or how could we get acceleration from the velocity of the object? So we have this truck. It looks like it's traveling at a constant velocity, and we can tell that because the distance between the oil drops isn't changing. Okay, if I were to construct a position versus time graph, it would look like this. So we're just putting the position down at every second. So at time 0, it was at 0. 1 second later, we can see that second oil drop. That's 2 meters away from its initial point. And then 2 seconds later, it would be 4, 3 seconds later, 6, and so on. So we want to look at how can we get the velocity from this. So remember, velocity tells us how the position changes as time changes. So hopefully what you can see here is that the position is changing by 2 meters every second. And hopefully you can notice that that is just the slope of that line, right? So the slope of a position versus time graph is, in this case, it's constant. Therefore, the velocity is constant. And so we can figure out what the velocity is by taking the slope, by figuring out the slope of that line. So we have velocity is equal to delta x over delta t, which is just 2 over 1, which is 2 meters per second. And we could graph the velocity. It's a constant, so every second it's going to be 2 meters per second. Okay, so pretty easy there. But then what about this one? So how can we construct velocity from this? So hopefully what you can see here is that the distance between the oil drops every second is larger, which means that the truck is not moving at a constant speed anymore. If we graph its position versus time this is the graph that we would see. Okay, and the issue here is that the slope is constantly changing. So that means velocity is not constant. So the idea here is how can we figure out what the velocity versus time graph would look like? So what we can do is we can find the slope of tangent lines at different points in time on the position time graph, and that would be a good estimate for the velocity at those times. Okay, and then we can predict what the velocity graph would look like. So here's what I mean by that. We could draw a tangent line at time 0, and what you notice is the slope of that tangent line at 0 is 0. So therefore, at time 0, the velocity must have been 0. He's not moving. He's starting from rest. Okay, I could draw another tangent line at some other point, let's say 2, at 2 seconds, and calculate that slope. And whatever that slope of that tangent line is, that's going to be the velocity at 2 seconds. Okay, and then I can do the same at another point. You could do it at every single point. Okay, and what we want to be able to do eventually is use calculus, because calculus will tell us the slope of those lines at every single point. Okay, any point in time that we want, we'll be able to figure it out if we can use calculus here. All right, so we find the slope of each of those lines. Slope at 0 is 0. The slope at 2 seconds is 2 meters per second, and the slope at 5 is 5 meters per second. And it looks like the slope is linear, right? It's increasing by 1 meter per second every second is what it looks like. At 0, it's 0. At 2 seconds, it's 2 meters per second. At 5 seconds, it's 5 meters per second. And so that means that the graph for velocity versus time graph must be linear, right? So that's what the graph for velocity versus time in this case would look like. Okay, so now we want to look at how do we get position from velocity, or how do we get velocity from acceleration? So here we have a velocity versus time graph, and it's linear, so it's similar to the one we just looked at. It looks like every second the velocity is going to increase by 2 meters per second. So velocity is not constant, obviously. So if we recall, velocity is equal to the slope of position versus time graph. Velocity is change in displacement over time, which is slope. If we rearrange that equation, we get delta x is equal to velocity times delta t. And this sort of looks like an area, right? Area is a length times a width. And in this case, our width is delta t, right? It's the horizontal axis, and our height or our length is the velocity. So what we can do to get displacement from this graph is we can take what's called area under the curve, figure out what area under the curve is. And anytime you're calculating an area that is above the curve, so here the line is always above the horizontal axis, you're going to calculate a positive area. If this ever goes below the horizontal, that means that we're moving in the negative direction. You would calculate a negative area in that case. All right, and so a question might be, we want to find the delta x, the displacement, for the first 4 seconds. So what you're going to do to get that is you are going to figure out the area under the curve for that time interval, so between 0 and 4. And so that's a triangle. Area of a triangle is half the base times the height. And so in this case, we're going to have half of 4 seconds times 8 meters per second, and that's going to give us 16 meters. Okay, so we ended up with 16 meter displacement in this case. So just like a second ago, we looked at a curved graph for position versus time. In this case, we had a nice linear graph, everything's straight. It's easy to find area if your graph is either linear like this or if it's constant or some kind of combination like that. Finding the area under a quadratic curve is a little bit more difficult, and that's where calculus is going to come in. So we'll eventually see how to do that also. Okay, so I just want to summarize what we're learning right here. We saw these graphs earlier. Given one of those graphs, you can determine either of the two, and we're going to look at some examples of doing that in the next video. But just to summarize, if you want to figure out velocity from position, you're going to take the slope. If you want to figure out position or displacement rather from velocity, you're going to take the area under the curve given the velocity graph. If you want to figure out acceleration and you're given velocity, then you're going to take the slope of the velocity graph. And if you want to figure out velocity given acceleration graph, you're going to take the area under the curve. Okay, so let's look at this example here. So a truck is moving at constant velocity for the first 5 seconds. The brakes are applied so that the truck steadily slows to a stop for the next 5 seconds. And what we want to do is we want to construct the position versus time, the velocity versus time, and the acceleration versus time graphs. So if you want to try this on your own, draw three different coordinate systems and see if you can graph what the position versus time, velocity versus time, and acceleration versus time graphs look like. So I like to start with the position versus time graph. Okay, and so this is what I ended up with. And what we can see is that for the first 5 seconds, okay, I didn't label the axis, but the first 5 seconds, the truck is moving at a constant speed. And I can tell that because the distance between the oil drops is constant for that first 5 seconds. So therefore, position versus time is just linear for that first part of the motion. Okay. Therefore, it's moving at constant speed. Therefore, the slope of my position versus time graph needs to be a constant. Then the truck is going to start to slow down. And so what I should see is the slope of my position versus time graph steadily decreasing. Okay, it says that the truck steadily slows to a stop. So my slope needs to steadily decrease until it's 0 at the very end. You can see if I drew a line tangent at the very end, the slope of that tangent line would be 0, indicating that the truck isn't moving anymore. All right, so now we want to construct velocity versus time given what we just found for position versus time. Okay, for that first interval, the slope is constant and it's positive, right? A positive slope. So what my velocity should be for that first part is it should be a constant positive value. Okay, then we see the slope of my position time graph steadily decrease. So then from there we should see the velocity graph steadily decrease until it gets to 0. And so this is what that would look like. So again, that first interval, we have a constant slope for position, which means a constant velocity, and then the slope for position steadily decreases, so we should see a steady decrease in velocity over time for the velocity versus time graph. Okay, so now that we have that finished, we should be able to use that graph and figure out what the acceleration versus time graph should look like. So as you can see, for the velocity versus time graph, we have a constant slope, or we have a constant value. What's the slope of that constant value? The slope is 0. So for that first interval, our velocity isn't changing, therefore we should have 0 acceleration. Slope of velocity versus time graph is 0, therefore acceleration is 0. Then we see a steadily decreasing velocity. It's a linear line. It's negative. So therefore acceleration should be constant, right? It's a constant slope, so acceleration should be constant. But since it's a negative slope, the acceleration should be a negative constant value. So then we end up with a graph like this. All right, it's hard to see the green line on my screen. Hopefully it's not for you, but you should see a green line going from 0 to sometime later that is 0. And then we just drop down to some negative constant acceleration. So that's what that graph would look like. All right, in the next video, we'll look at a few more examples of how to construct these graphs and how to interpret them.